You ready?
Sure. Have to be. No choice, dude.
All right, I think we're ready to start. Gives me great pleasure to introduce Jan Peters, Professor Jan Peters. He's co-hosted by Drew Bagnell and me, who's over there. He's still here. So Jan and I have known each other for over, I guess, about 15 years now, since I guess 2001 or so. And I always remember Jan as the guy I would get a beer with at conferences and bitch about how bad the WAM arms are. And we still did that today. So some things never change. But Jan is one of those people who does everything, soup to nuts, develops fantastic theory, builds algorithms, writes code, good code, some of which I've used, but is very passionate about getting things running on real robotic systems. And that's something that you'll see in his talk today, real things doing interesting stuff. So it's a real pleasure to have Jan here, and I think his work and his philosophy will echo here at the Robotics Institute very well, because we're also very passionate about getting things running on real robots. So Jan has a very long talk that he promises will take about an hour, because we have to go to the post-seminar reception right after this, right, Shervin? Yeah. Shervin, yes, at 4:30. So if you have burning questions, you may ask them, but you're just delaying all of us from going to the post-seminar reception. So please don't. Without further ado, Jan Peters.
Well, thank you. Well, thanks so much for the introduction, Sid. This was really the most special introduction I've gotten in my life. For me, it's quite amazing. Last time I was in Pittsburgh was actually when I was a prospective PhD student in 2001. And that I wouldn't come back until now. Well, it's quite surprising, but also it's quite amazing, quite cool to be back finally. So I'm going to talk about motor skill learning and really about our complete story. And I will, as I ended up instead of Pittsburgh, ended up just 6 miles south of Hollywood. So allow me to start with a small movie clip. Obviously a movie clip which we all have seen, which got many of us into robotics, since it shows just the one thing we all of us crave, right? Robots which are finally in the shape to do all of these things. And obviously the next thought for all of us is, well, how can we actually program all of these behaviors? And well, that's the moment where we start, oh my God, this is gonna be really hard. And well, what do we have? We have uncertainty in all the tasks in the environment. We have adapt to humans that interact safely. And we have a programming complexity which is way beyond human imagination. So how can we fulfill Hollywood's vision of future robots? Well, we all know the classical answer: smart grad students. We put them in a cellar, give them pizza, Coca-Cola, end of the semester, task fulfilled, problem solved. That particular problem we have in back, and we have a primitive for exactly that problem. Only problem is, next batch of grad students comes in, and we're starting again all over at square one. So quite clearly the challenge for us, post already in the 80s, and where Chris started the pioneering work in that area, is that, we need to learn these things. Unfortunately, this learning part turned out to be quite complicated. Since what the machine learning people promised us of, we're just going to give you one black box, you throw in data, and on the return you get whatever behavior you want to have. At some point that was called a neural network, then it was called a kernel machine, now we call the neural networks deep networks again. But we always end up with this scenario, and this is quite clearly not the one which we in robotics can actually crave to have. But rather, we need to really figure out how to build skill learning architectures that are suitable for the problem and which leverage as much as we can on what we can give it in terms of physical insight and in terms of knowledge on the world of robotics. So we really need to develop task-appropriate skill learning approaches. So that, of course, requires us to think about 3 questions. And hopefully at the end of that really have this, and obviously I'm only going to tell you, well, our feeble first steps into the directions. First of how we can actually develop motor learning methods that scale to actual robots. Then how we can build, learn primitive basic skills at a speed so that that it's not going to be, well, beyond the lifetime of a robot, which for the Barrett WEM can, for early table tennis trials, quite easily mean just a very few trials. And then you have to exchange the complete cable drives. So you really want to learn safely and still fast. And then how can we compose complex skills with these elements? So in this talk, I will, after a short introduction, focus on these three questions. And if we still have a little bit of time, I will also tell you a little bit of how we can adapt such skills to humans, and some newer work there as well. Now, of course, the first part of the introduction is going to be pretty boring for anybody who's worked with Chris or with Drew, since it's going to be a very basic introduction of how we, well, do learning in such systems. And, well, for that, first think of, well, a robot with a paddle here, with a string and a ball attached. And we quite clearly have an internal and an external state for that robot, where the internal state is the proprioceptive state, while the external state would be, for example, the ball position velocity. But we want to send motor commands, meaning torques for the robot arm, or, well, muscle commands, of course, for this human robot, as actions. So we have actually quite a high-dimensional mapping problem. But in the end, this is exactly the mapping which we need to learn in the end, since what we want to have is a policy from states to actions. And obviously, we always have some form of learning signal. We have a teacher, which evaluates the performance and, well, rates it with a rating R. And then we have the environment, which obviously changes its state whenever we have done an action. And classically, in a perfect world, we would all do this deterministically. But as we all know, the real world is stochastic. Now, classical AI tried to come up in the 1980s with one set of rules, which would allow us to, from these rules, by doing some inference, always figure out what are the right actions, and that would be intelligence. We all know this failed. But instead we really, well, needed to learn is to, well, what we still want to have is somehow a mapping from states of action to actions. And can we actually use, well, model this by a deterministic function? But I think whenever you do learning, you need to try out new things. You need to make somewhat mistakes. And for that, stochasticity becomes crucial. You need stochasticity, first of all, for exploration, since if you try the same thing over and over again, that obviously means that you're not going to explore new things. And in some cases, even for simple modeling issues, for persistent excitation, you need to add stochasticity as well. People who have taken basic computer science classes will remember maybe the times about quicksort, bubble sort, that was basically the same, except for the stochasticity about the pivot point, and how that turned the slowest of all sorting algorithms into the fastest. In a similar way, it can ease very frequently the algorithm design when we add a little bit of stochasticity, and hence force stochastic policy. And in some cases, the optimal stationary policy, for example, can be stochastic. And we are in many cases very interested also in modeling the variance of the teacher, because it is quite informative. When you for the first time steer a new boat, usually the stochasticity in your tremor will actually give you a sensitivity analysis that you figure out very quickly of how you're supposed to move the steering wheel in order to have the boat move incrementally in the right direction. Hence, we very strongly push forwards using stochastic policies, which are probability distributions over the actions given the state, which have some parameters which allow us to do learning. Now, obviously, we're not just interested in one state, in one action, but we're interested in whole loops of them, and which gives us, well, state action trajectories. And using these assumptions, we get path distributions and path rewards. And, well, what is learning? Well, learning obviously is improving yourself. So this shows a really old example of ours. I guess here in the US, I do not need to explain what T-ball is. In Europe, you always have to. And what you see here is every 15th takeout from Sarko's arm trying to hit the baseball with a toy baseball bat. And it's getting a reward based on the predicted distance the ball which will travel, and it gets a punishment for the amount of joint movement. So in this case, these rewards, well, they become scores, and we're trying to optimize the expected scores of the teacher. And after a couple of hundred trials, usually around at least 300 trials for that old algorithm, it manages to converge quite well. Turns out there's an American Association for T-ball, and they say a kid of the age of 4 to 5 actually needs around 1,000 and 1,200 trials to properly hit a baseball. Not sure how true this is. I've never managed to do it so that you guys would call it proper, but that's the European part. So now, using these assumptions, let's come up with the learning scenarios which we need. And just like we humans are bootstrapped by a lot of things. We're bootstrapped by the reflexes we are given at birth. We're bootstrapped by when the cerebellum kicks in and helps us to fine-tune our movement. And this whole process, well, gives us a lot of priming before we can actually do motor learning. Similarly, we want to bootstrap things by first reproducing demonstrations and subsequently doing self-improvement. And for reproducing demonstrations, we actually have a clear metric. Since if you use a stochastic policy, you end up saying that you just want to be as close as possible to the distribution of trajectories which you've observed with the distribution of trajectories which you can generate. And assuming you have all the statistics of your trajectories, you can actually make this one-shot learning problem. If you have some unobserved variable or hidden variables, it obviously becomes more difficult. You need a model. So in this case, we only need to adapt the policy parameters, and well, in many cases can even be completely model-free in one shot. In the bandit case, it's easy to grasp. It's just we get a distribution of our state-action pairs. It's obviously more complex. It's obviously more complex when there are sequences where you get a more complex distribution. So, but if you take a general reward function, which we obviously need in the next step, we all know we didn't graduate with a PhD from primary school because we couldn't all do it by imitation, but needed this painful experimenting and research, which you need for self-improvement and homeworks, of course. So, for that, you need a general form of a cost function in here, and can no longer use the log of the two probabilities. And what you should notice, though, is that in this case, the cost function no longer includes the notion of data. In fact, you only have the distributions which you're generating and the reward which you, well, obviously also get from the system, which leaves you with very few choices. One choice is learn models. That's what, for example, Chris started already to pioneer in the 80s. And learn forward models, and then you can actually do a hell of a lot. But you're also limited by the model because a small error in the model can ruin your policy. We at one point learned forward models, and this forward model gave us the wrong curvature on the velocity, which basically meant we suddenly had negative friction, which for this optimizer meant, oh, I have an energy pump, which also meant that I had to recable the WEM an hour later. So it quite clearly something very, very bad which you can learn from a small error in the model, which was even in terms of just an error in terms of the slope, and not so much in terms of the actual predictions. And similarly, the reinforcement learning community has mainly focused on trying to take dynamic programming and turn it into algorithms which work for larger state action spaces, which requires somewhat to do, well, in the context of continuous states and actions, to treat things quite heuristically. And it has failed to, for example, achieve any kind of guarantees there for, well, working in the kind of systems we're in. And particularly difficult for ARMS is that you cannot really fill the state action space up with data, which is even for the classical algorithms there a need for well, convergence, for example. And finally, well, there are policy gradient methods, which is where we got started with originally, and that basically allowed you to do only small updates, and hence slow convergence. And then we stumbled upon something which was somewhat different. And that was the quote in the psychology literature that when humans do the same problem over and over again in a stochastic environment, they actually don't just go for the one thing which has worked really well, but they will do some success-weighted reweighting of what they've done in the past. And so we found this was really cool and interesting, and it somehow intuitively made sense because it means, can we just match our policy, our new policy, or our new trajectory distribution actually, to the past trajectory distribution just reweighted by the rewards received after each action. And in the bandit case, you can again make this nice and visual. Let's say you have good actions, all shown with the pluses, and bad actions with the minuses, generated by this policy coming from an imitation. Well, in this case, the next policy should obviously grasp the pluses in all the states where we have many pluses. But if there is a state area where we have only bad actions, we should nevertheless try to reproduce the bad actions there so that we keep on having safe exploration. And there are many, many frameworks which relate to this, as we figured out over the time. The very first time we applied this was way back during my PhD at USC, but we hadn't totally figured out the theory behind things. And we were suffering, as probably many people in the room, from the DARPA legged locomotion program and Little Dog, which basically at that time fell over whenever you stepped on a bad foothold. We learned a foothold placement policy where we used reward as a slip as a reward. And if it slipped little, then this was good. And it learned quite efficiently the first policies until we came up with a more tweaked approach, which was even better. But it showed us that this basic insight worked quite well, and that we could probably generalize it from the bandit case to the trajectory case. So in the trajectory case, this would just mean taking the distribution over trajectories, which we have observed, reweighting it by the rewards, and then matching the trajectory distribution, which we are generating with our policy, to this one. You directly recognize, oh, this looks nearly the same as reproducing demonstrations. Just that the rewards now, they have to be positive in this case, become an improper probability distribution, meaning a probability distribution which doesn't necessarily sum up to 1, and basically have the same function as a probability of being good for that particular trajectory, or actually for these particular actions. And what's even nicer, it gives us an EM-like algorithm where we are guaranteed to go at least to a local optimum. Now for us it was particularly helpful because we can choose, of course, our stochastic policy to be in particular forms. Like, let's say we've chosen to be linear in our features and our parameters and have Gaussian noise. In this case, it boils down to taking the actions we've taking the rewards we've received after these actions, reweight down the actions, and project it onto the features. And suddenly, we've opened the whole box of regression methods for regression-like approaches for the policy update step. And for us, this is allowed to develop now using, different kinds of noises. Is either just a state-independent noise or state-dependent noise, or assuming there are some hidden variables which need to be estimated, or using a kernel-based method to come up with, every time, a slight variation of the same algorithm and to get really efficient policy updates. And we're also having some, newer work which unifies this all in a kind of new program. So I hope with this I've given you a glimpse of how we do policy updates, how we can initialize permutation from demonstrations, and how we can subsequently do self-improvements using this reward-weighted regression. Now I'm going to talk a bit about how we can learn basic skills similar to humans. And for that, of course, we need to leverage things a bit more on the knowledge we actually have about robotics. And what we have in robotics is quite clearly, this mapping from state to action, But we quite clearly have a lot of stuff which we can move into learning of models, like learning of inverse models, which help us with execution. So that we can actually just work with desired accelerations coming from primitives. And we obviously want to have many behaviors which we can reuse in different scenarios and select among based on the context. And now I'm first going to talk a little bit of how we can learn elementary behaviors, and subsequently how we can adapt them to new situations. So for that, we are have been working on a series of different trajectory generating policies. And this was actually one of the earliest forms. Right now we have a probabilistic version which is better, but would probably kill this talk since it would be talked completely by itself. But in all of these versions, we have one thing in common. We have task parameters which allow us to use learned behavior in many different situations. And we have shape parameters which allow us to actually learn certain styles of movements and restart them in different scenarios and situations. So first, let's take a task where we learn by demonstration. And what you see here is how the robot is being taken by the hand. And this is this ball on a string scenario. So that's why it's so fast. And the key part is to first bring the ball into a limit cycle where you can keep it, and subsequently to keep it there. And here you see the reproduction. For us, this was actually quite surprising that the demonstration completely sufficed for it, since we had actually a couple of months before that first tried to do the classical approach of hand tweaking and doing it all by modeling and classical engineering, and we actually never got it to hit the ball more than 3 or 4 times. And so we were actually starting with a very, very low baseline back then, and we're quite surprised that the imitation of that demonstration worked out of the box and reproducible for different demonstrations. Now, of course, that is normally not enough. Just like usually when you learn, let's say, a sport like tennis teacher takes you by the hand, shows you this is a forehand, this is a backhand, and then you are faced with a ball gun. Well, you realize it usually doesn't work for the next 300 trials. And for people with poor motor skills like me, substantially longer. So normally you fail when you when you're trying a new skill. So here we have a ball in the cup task where we again have a demonstration, and just the reproduction fails because the spike in the acceleration which you need cannot be properly reproduced. And subsequently, you do see a trial by trial. You see a self-improvement, and after about 40 trials, it gets the ball into the cup for the first time. And after about 90 trials, it gets the ball into the cup about 100% of the times. And so we asked ourselves, of course, how does this compare to humans? And my student Jens Kober, he tried it out on all of his cousins, and he has quite an extended family. So it turns out cousins at the age of 6 to 8 did not manage to learn it at all. Cousins at the age of 10 to 12 managed to learn it within 30-something trials, which is already a bit better than our algorithm. And cousins at the grown-up age managed to usually learn it within 3-4 trials. So it seems to be only me who took about 3 months to learn it. Two big differences though. The cousins cheated. Our robot hasn't done this a single time. And chocolate as rewards seem to be quite more stimulating than numbers. So next, we of course want to reuse these primitives in new scenarios, in new situations. And that requires us to map context, which can actually be arbitrarily complicated, to selection of primitives and reparameterization. And for that, we should remember that for the reparameterization, we can actually use these additional parameters, since so far we've mainly been focusing on these shape parameters. One of the first things which we did with was to do dart games. Now, I think that's probably not a very American thing. I actually don't remember. Do people play dart games in Pittsburgh? They do? Okay, in the UK, people get all excited when they see this. So Dart...
All the time, yeah.
Okay. So what you see here is an around-the-clock Dart game, and the yellow dot tells the robot simply where it should go for, just always reusing the same kind of throwing primitive. And we've actually did this with a couple of robots. It looks most fancy with the humanoid robot CBI, and where we did this in Japan. But with an industrial arm, you actually get to a reliability that you can play against the human, and it beats me all the times. We also, so then using now kernels between contact distribution, perspective contact points, we can also generalize now grasping movements among different objects, and also on different ways of going for the same object. And using different kinds of cups, we've also used this now for pouring. So where we have different containers, and also in some cases different cups, and reuse the same scenario there. Then you can have two robots share rewards. And well, here's a robot throwing the ball, another one catching it. Initially, they don't match at all, and after a while, they actually align quite well where the one guy throws, such that the other guy can catch it. Where they just, the only thing they share is actually the knowledge about each other is the reward. So with that, I hope we have to somehow shown that we can actually learn some basic skills. Now let's look at whether we can compose something. And for composition, we're really at the baby steps. Since composition obviously directly hits now a border of quite a few fields which are really complicated in control. Like if you were doing, for example, sequencing, you're directly very close to hybrid control, where anything which was easy in linear control theory becomes already complicated for a hybrid control system of two linear systems which we would perfectly know how to control. So composition with selection, superposition, and sequencing is a really tough problem. But I'll show you the steps which we have been doing over the last couple of years. And for that, we really can now plug all of these things together, including the execution part, which I haven't been talking about, and really learn first just superposition, and then I'll quickly talk about selection, and finally about sequencing. So the naive approach would be, let's just learn a couple of primitives, do some self-improvement, and on the repetitive targets by reinforcement learning, and then generalize between targets and hitting points. And well, here you see some demonstrations, hopefully. Okay. And sequentially, the robot gets a subset of these demonstrations, and from these tries to span the space of incoming balls observed in the data set. And well, you can now learn from these primitives, and you can mix them based on a reweighting on the incoming ball. So having a gating network is a reweighted combination of these primitives. The initial policy which you get from this already has quite a good success rate with about 69% return rate of the balls. But well, obviously that's not enough. And so we will need self-improvement in a second. And well, further training. So the reason why we need this is you can see actually in the ball distribution, since the test set doesn't completely cover what the training set has captured. And so you can actually aim the ball gun at a location which wasn't part of the training set, and wasn't also on the size of the training set. And after actually quite few trials, it manages to cope with the part. After well, about 60 trials, that place, which was at 0% success initially, gets up to 79%, and all over the player here against the ball gun managed to go up into the 90-something percent of success. You get a different activation subsequently out of the primitives. So quite a changed gating network, where you always see here the most activated and the second most activated that primitive. Finally, here you see the robot playing against its maker, and I would claim they're about equally good. So now I said the naive approach. Why was it naive? Well, we realized it was naive because we figured out that the distribution of balls which we got helped us substantially. Since they were always coming roughly from the same direction, there's a big table tennis table in between, and you would never have you never had the situation that you actually had to do a non-convex combination. So we decided, as one of the next steps, to place an obstacle into the space. And with the obstacle, we obviously need, for a ball, you need a bit more than just an obstacle. We henceforth put the ball on a string to have a tetherball-like task. And in this case, convex combinations of primitives will actually fail, and you really need to make a proper selection and decide whether you want to hit to the right or you want to hit to the left, and really need to fulfill the selection component just as well. And so why was this so problematic? Well, we can actually see this quite well when we look at learning. And here these would be kind of two different activation axes of the primitives. Then it would focus the learned primitives, or the two primitives learned here, it would focus them on the same distribution of data, and it wouldn't actually split up. So it becomes quite complicated, in this case, to deal with this scenario. And we figured out that there is a very simple trick by simply forcing the responsibility of the primitives to be limited by limiting the entropy in the gating network, that they split up and primitives start to specialize. And in the context of tetherball, we can actually now nicely reduce the number of primitives, while at the same, where you see here the number of options going down quite fast, being pruned, and while at the other case, at the same time, we get a faster learning response on the reward. So good performance while having fewer primitives and an automatic subselection of primitives. So finally, we are of course not just only interested in robot table tennis, but we are really interested in manipulation. And we have put Oliver Krömer here since up to 2 days ago. He was on the job market, and I was hoping he would get a postdoc here. Now he already accepted one from USC. So he's a PhD student doing heading our manipulation. And you can actually do grasping with these primitives in a pretty similar way, by instead of trying to figure out the right velocities and right hitting points, to instead go for reusing these primitives such that they can do the right kind of obstacle avoidance, the right approach direction for an object, and adjusting the fingers of an object. And that you can generalize quite well even between objects if you map the primitives rightly. Now, manipulation finally requires us to do one thing which in table tennis we never really got to, because in table tennis there never seemed to be sequences more than 3 where you could really get to sequencing so far. But in manipulation you really need phases, you really need to switch primitives, and you need to know to which primitive you want to switch to in the next stage without taking an opponent into account or anything like that, but really just based on the object and your manipulation action. And Oliver has done a lot of things in this context, including all kinds of block stacking manipulations that she learned. Learning fun things like cutting an eggplant, learning sequencing of pepper mill tasks, such that it would spill proper pepper, and well, here you see some of the results, some speed up, some in real time. And these are, by the way, our 5-finger DLR hands. So, now, I don't know how I'm doing in terms of time. Doing all right? So then in that case, I will quickly talk about one topic which is kind of becoming more and more important to us. And it's actually something which Sid has been telling me for ages. So what are you doing about the human? We're slowly getting there, but it's, well, you'll see. So for table tennis, we quite clearly had 3 problems at the moment. One is our workspace is incredibly limited. Imagine your robot arm and you're nailed to a ceiling. It's not fun to play table tennis that way. The second thing is that robot arms, especially the Barrett WEM that has a 2-kilogram wrist, you need to accelerate this wrist. You cannot just do what a human does, kind of a flick, where you release your muscles and they give you this catapult-like movement, which allows you to already out of just your wrist already create an enormous acceleration. And, well, limited reaction time. Well, the last one is maybe counterintuitive, but we get very few frames, and we can only determine the amount of spin in the ball after this hit the table, which basically means that we can have by a 5-degree error in the spin axis. You can have a 90-degree change of the direction of the ball after it goes off the table. Now, only after this bounce off the table, we can decide between a forehand and a backhand. And really be certain that this will be the case, just based on the human trajectory. Now, the first 2 problems we can only solve technically. And there we're only at the simulation stage, but what we're basically planning is to take an arm, which is developed at the Technische University of Darmstadt in one of our neighboring groups, which is muscle-based, and we want to place it on basically a linear axis, 2 linear axes, such that we have a mobile base and really can cover a wide range of situations. And the muscle-based actuation should help us to create the really high accelerations, which we also would like to have such that we can do a flick in the hand. The third problem, though, is the limited reaction time, and that is one we share with the humans. Just for humans, it has a totally different reason. What you see here is a baseball game from the only other nation but this one which plays baseball, which is Japan. And this here is the last moment where this baseball player creates any vision-based action on where to hit the baseball. So quite clearly, he will probably not have estimated this just from this short piece of the trajectory, but much rather he has done more. And what professional table tennis players actually told us is, yes, you need to look at the opponent. You shouldn't actually look we are trained not to look at the ball. So that brought my PhD student Jikun Wang to the idea that he wants to infer from the human's action, in this case himself, where the human will shoot the ball. And what you see here is the ball 80 milliseconds before he hits it. Here it is about 120 milliseconds before he hits it. Sorry, 180. And this is about 320. And well, each of these times he can now predict where the ball will be shot. And the really impressive part is that 320 milliseconds before he has even hit the ball, you can predict with an accuracy of about 30 to 40 centimeters where he will shoot the ball. And obviously, in the moment where you're at 0 milliseconds, it drops very, very quickly. If you have already, since you have here already the forehand, or whether it's going to go be whether you can take it by forehand, a middle strike, or some other kind of a movement. So it really gives you a huge advantage. Here you see again, here you see a video of how different people are taking turns at playing against the robot. Now, at some point, we realized, of course, opponents are one thing. Now, what about if we do want to help a human? Now, this here is a mock-up. This is what we would really like to see. A third hand helping a human worker. Since, as you know, while Americans may still have a stable population growth, we in Europe, we go like this. So, with other words, our workers will become older and older, and we will need and quite frequently. And one hope, which is even supported by our industries, that we figure out how robots and humans can safely work together. And this kind of a third-hand scenario with, well, here now this box example, has been quite a driving force for us. And I apologize for this slide, it should look much better. So what we've then realized is we can look at the primitives and primitive selection also from an interaction point of view. If we now try to infer from the trajectories of, let's say in this case, 2 human demonstrators, what kind of primitives they're executing. So this could be here different high five movements. And then we would get a distribution over possible motor primitive parameters. And then in this case, if you observe just a partial trajectory, by conditioning on the partial trajectory using our known primitives, we can complete the primitive and, well, for the high five task, quite nice to reproduce it. And that we are currently transferring now into manipulation. What you see here is a video which should run faster of, well, a box being assembled together jointly by, well, our master student Marco Everton and our robot, where he's literally trained this up in about half an hour of work before that. And, well, he obviously pretends to be an old man, hence he's so slow. And yeah, in this scenario, the robot always interacts in the way of how he thinks the actions are supposed to be. We've also had the reverse scenario, where the robot had to assemble the box and the human had to hand the pieces. But yeah, I think this is probably going to come next in that video. So, oops, that part I wanted to not include. Well, I don't know why this turned on. So that would be too long. So now let me give you a quick outlook. And, well, we clearly don't care. Well, table tennis is kind of our Drosophila. It's kind of this little fly of the biologist. We love trying out things on it. And we will keep improving this scenario for quite a bit. But I think the methods we're developing, we want to make them as general, as scalable, and as modular now as we can do, so that they can really find their way into application. And with this, for this, we're collaborating with the companies like Honda Research in Offenbach in Germany, as well as Bosch and ABB. And there's really a key insight there, and that is that if we can basically, if a product costs, well, less than 50 euros and is produced less than 10,000 times, you can't do this in Germany by programming robots. You really need robot learning in this context, and simply because the cost is too high. And obviously other scenarios like, well, us having a personal robot or assistants in hospitals would be great applications. And, well, also a quick outlook on other things we do which relate to this. So I've told you mainly about our robot skill learning story, but we are also, of course, venturing all over robotics. We're developing machine learning algorithms, and we also quite interested in some of the biological inspirations and also some life sciences applications. And just to give you a few examples, well, graph manipulation you've seen. Here, these 2 videos should run. I don't know why they don't. This is our tetherball setup, where we have different algorithms now play against each other. We actually want to really create a map of all reinforcement learning and imitation learning methods applicable in this scenario at some point and have them played against each other. Locomotion is interesting to us. We do a lot of tactile sensing. We have a huge EU project for that. we're interested in well, nonlinear control, and obviously for table tennis we need high-speed heat vision. And it is playing finally. So here's the tetherball scenario. So this is the player which I described, the tiny extension with primitives now being forced for parsimony. Then we're obviously developing way more machine learning approaches and reinforcement learning, but also special regression methods which can deal with discontinuities like you find them in stiction, which is quite important for when you're trying to still learn better inverse dynamics models, for example. And also things like Bayesian optimization and many more machine learning algorithms. We apply some of these methods together with Moritz Grosse-Wentrup from Max Planck and PCI group in the context of rehabilitation of stroke patients who have an implanted ECG grid, and also with the brain-robot interfaces with again patients this time with an EEG. And we're quite interested in how humans play table tennis and have some interest in how motor control actually works in humans. With that, I'm at the conclusion, and I hope to have made the case to you today that motor skill learning is fun and interesting, and we have made some tiny contributions on how to do imitation reinforcement learning there. And we've gotten as far as table tennis, tetherball, manipulation, lots of other things. And we hope that many other interesting research topics profit from this work. With that, I would like to thank for your attention. And these are all the people who have been helping me with this over the last 7 years. And hope you have lots of questions now.
All right, we have time for some questions.
So you mentioned in the first slide itself that stochasticity was important in learning.
Yes.
But every time I talk to people who are, let's say, working on autonomous drones, self-drones, or autonomous cars, they get really scared when I say we will learn, try to do imitation learning, or I'll apply stochastic policy, which will interact and learn. And they're like, no, maybe not. We'll not try that. So what do you think? Can we solve those problems where if you make a mistake, it can be really catastrophic? Can we ever reach that kind of deployment scenarios?
Yes. I mean, for some scenarios, this is a really question which we can't easily solve. How do you do this if a human can really be harmed? I'm not sure how I would answer there. For scenarios where, a drone, where hopefully a human, unless it lands into somebody's garden or on somebody's head, can really not be harmed easily. In this case, I think we should really focus on creating proofs for stability on when this method works and how many samples you need for this. Now we look at the moment at very simple scenarios. So we look, for example, in the context of just learning stabilizing policies. We look at after how many samples we can get a guarantee with a certain probability. That's one theory scenario where we have now a proof sketch where, for a limited class of systems, we can actually prove this. I think that's the one answer which we can give in this context to, let's say, drone people. Sometimes stochasticity, though, can be mild. If you just add a tremor to something, to a movement, and this movement already has some passivity, then this tremor is not going to kill you. And so as long as you have a control, and we usually have specific parameters, as for example, variance parameter for the linear Gaussian policy, linear in features with Gaussian exploration policy. There we have a clear parameter telling us how much exploration we're doing, and we know that we are very unlikely to do something crazy. And that's kind of the third answer to one question. So depends on the scenario. Other questions? So boring?
When you're talking about these parameterized trajectories, some of the time it seemed like you were talking about using them where you were controlling a joint with a trajectory, but other times is it always joint based, or do you have something where the trajectory is like a workspace trajectory or something like that?
This is a really good question. So the humans quite clearly learn some tasks in joint space, other tasks in task space. So task space for us is usually the retina space, then even where we, for manipulation, becomes quite easy to do things in retina space, for example, if you really do reactive control. But for table tennis, to do this in task space would be a disaster, because you would do some really awkward pushing motion unless you really figure out some very interesting forcing function for distributing the load of that. So we actually have learned both kinds of generators, and for some cases it makes more sense to go for task space movements, in other cases for joint space movements. For the task space movements, though, there comes a whole enchilada that the execution box becomes much harder, because you're no longer just learning an inverse model of your body, but you're actually learning a whole operational space control model. On that I did a lot of work in my PhD. I can send you the IJR paper if you drop me a line.
I guess I'm thinking about the darts one, where it looked like you were adaptively changing. I don't know if you were.
No, for the darts one, our policy generates joint space accelerations, and it gets modified its parameters, its hyperparameters, its task parameters, based on where in the goal space it's supposed to throw the dart. So there's a very nonlinear mapping there, but every example which we've had basically became part of the policy, since we used this non-parametric version of the reward-value regression, the cost-regularized kernel regression. And that gave us, as a non-parametric way of now mapping, but reusing that primitive for all the different scenarios, including also all the ones that's interpolating in between.
Thank you for the fantastic talk. So, referring to your table tennis scenario, much of what you've shown, I think, is about returning the ball. Whereas sort of winning in table tennis is as much about strategizing
Yes.
the longer range plans as it is about sort of returning the ball. How do you envision your learning algorithms to sort of extend to much longer horizon learning, where you need to not just learn to put the ball back, but to set up the next few shots, 3, 4, 5, and such that you actually end up winning the point rather than just hitting the ball back?
Yes. So quite clearly, this sequencing has to be one of the next steps. So far, we have only looked at humans and tried to recover human cost functions with the inverse reinforcement learning. For up to 3, I think the longest planning horizons we could find in humans are 3 steps. And it seems that actually very few parameters play a role for which make a difference between an expert human and a bad human player. Here, one of them are table preferences, and they usually have to do with the fact of how good humans are actually at the basic motor skill, and not so much about strategies. So if you're good already, then a good strategy, it will be easy for you to play a good strategy. If you're bad, you probably know what a good strategy is, you just can't play it. And so it will change the reward function, that's for sure. And you need to, of course, now remember, add in to your gating network the memory of your last stroke, and also the predictions on the opponent. And again, the opponent prediction needs to take into account a little bit more of what you have been doing, since it may become more aggressive.
At the beginning of your table tennis example, you said there were 25 loaded primitives. Where did that number come from? Is it just automatic clustering, or?
So we really originally tried a lot more primitives, and it usually turned up that in the 20s or 30s sufficed. No, we basically initially had also that we let it prune, and if some primitives were not activated in the gating network, then they could be dropped. Just on the real robot, you don't want to prune among 300 primitives, because for the buried WEM that would mean, I don't know, 50 times recabling, until you actually have pruned everything down. But the pruning happens automatically out of the reinforcement learning, out of changing the gating network.
Is the reward function designed by hand or also learned?
Okay, now that's an interesting question. So up to now, our reward functions have always, in everything I showed here, were designed being given by a human operator. And they were obviously designed to have good features such as, like, let's say for the T-ball, you wanted to punish very fast joint space movements because otherwise the system would try to hit as hard as possible and break the joints long before it was good. While you wanted to obviously reward good hitting behavior. Now, that's of course very insufficient. So these days, what we've developed is a class of algorithms which we call active reward learning. They've been published in last year's RSS and are now in the review at Autonomous Robots. And there we actually ask humans for scores. The human just gives a subjective number. And humans are really, really bad to give subjective numbers, it turns out. So you actually need to learn a model about how humans evaluate things. And that gives you then a relatively fast to good reward function. So you can actually recover the reward function from, can recover something which looks very close to the reward functions which people in grasping say are good grasp quality measures in the grasping scenario. And we had this in an iterative grasping scenario that it would learn this, and even when it would learn from these scores the actual grasp quality measure designed by Maximo Roa for the DLR hands would recover the exact same one, surprisingly. And in one of the experiments then where we used this learned measure then to show that it worked well, one of the fingers of the robot broke and we didn't notice it. And suddenly it learned a different, it modified this function, and we ended up still getting very good grasps. So this can work quite well, and this is actually for us a hot topic now to become more automatic about the reward functions.
At the very beginning of your talk, you mentioned an example of trying to learning forward models and stuff like that. It's a great example and it shows exactly what happens. But right now, one of the questions you said we want to run, we have 3D motion pyramids, we want to figure out which ones are good or bad, but we can't actually run them on the robot because that causes problems. Right?
Yes.
So there's some obvious trade-off here where you would like to maybe stimulate all these motion pyramids in simulation, see which ones you're dynamically are good or something like that. How do you trade this off? Where?
My first hope would be more reliable robots. So I would rather give this to the mechanical engineers. But obviously a forward model can help us to prune as long as we don't overfit it. It's a fantastic tool. We're also working on algorithms which make use of forward models. We usually try to go for forward models which introduce stochasticity then, and more stochasticity than the actual system had, which is one way of how we can force our system to become more stable there. And this is something which is relatively well known in the reinforcement learning community, since the NRing made it famous in the learning community. The simulation guys knew this, I think, in the 70s, that adding more staticity than you have in reality gives you more robust, optimized solutions.
Just on that topic, have you tried applying some of the skills that you've learned on one robot to another instance of the same type of robot to see how generalizable they are?
So far, only within tetherball, since that's the only time where we have two robots of the same kind in our lab, and there we had the same policy playing against itself and showing that on both robots it would play equally well. And that's also where we're doing the algorithm shootouts now, and where it's hopefully in the foreseeable future we can ask even people to submit algorithms and see how they do, so that we finally become evaluatable in the reinforcement learning domain.
Predicting what the person is going to shoot the ball, is that generalized across people?
Well, you saw different people playing against the robot there. I don't know how well it generalizes among people, but given that it's based on the arm movements, and that all of them were among different layman players for sure, if there is a, well, let's say a really professional player from, let's say, China who knows how to hold the hand such that nobody can recognize what the racket is, but where he will hit the racket even against the ball in the future, I doubt that it will generalize there. You will probably need to turn it then into a multitask learning problem where you need to first figure out which player type you have. But among a layman player, I think it generalizes quite well.
So in the box assembly scenario, I'm wondering how much of the behaviors of robot is predefined, how much is computed on the fly.
So this is really at the moment a box, a complete box where we showed the behavior. We gave it exactly one piece of help. So we gave it two pieces of help. One piece is we omitted the vision problem by putting markers, which gave us the more accurate human trajectories. And we helped it with the segmentation by always having a very clear stop signal. That you always would not, that during the demonstrations of the whole task, the two humans would always would not go very, very fast, but they would do very slow demonstrations. Everything else happens automatically. So segmentation, learning into primitives, and then learning this joint distribution over the two human primitives, and then the conditioning on one human so that the robot could take over the option of the other, the human.
Of assembly, the box, for example,
That's
this piece
extracted from the demonstration. So, but it actually recognizes the primitives. So you have a probability that after this primitive, another primitive gets activated. And you have a probability, obviously, that given these, given, let's say, my movement so far, this will be, well, let's say, a handover motion. And so you take these two, and now you have, of course, the joint probability given the past activation and the the complete pair of the trajectories, and then you fill in what knowledge you have, you condition on that. And that gives you the distribution of the possible motor primitives. There, for the for the classical DMPs, we would just select the maximum a priori, so we would select the best one. In the newer version, which we have already, we would now use the mean for it, and would use the mean behavior.
All right. Thank Jan.